This is Professor Rogers. In this presentation, I discuss multiple ordinary least squares regression. This technique allows us to have two or more independent variables in our model. I expand on the example used in the two-part video series on simple regression. With simple regression, I use state-level data to regress the log of the violent crime rate, my dependent variable, on poverty rate, my independent variable. The following results were found. The slope of the line was 0.05 and the y-intercept was 5.10. Based on a standardized beta of 0.39, the relationship was determined to be moderate and positive. The significance level met the criteria for 0.05 level significance. In fact, the p-value was highly significant with a value less than 0.01. The model explained 15% of the variance, based on the r-squared of 0.15. The model as a whole was statistically significant. I want to add another variable to my analysis. I do not think that poverty is the sole cause of crime. I think temperature might be involved. Crime rates are higher in southern states, and I am wondering if there is perhaps some association between temperature and violent crime. I need a model that can account for both the effect of poverty and the effect of temperature at the same time. Here is the output from the regression of the log of the violent crime rate on temperature. The betas give us the parameters for the equation of the line. The slope is 0.019, which I round to 0.02, and the y-intercept is 4.834, which I round to 4.83. The standardized beta indicates that the relationship is moderate and positive. The significance value of the relationship is 0.003. 0.003 is less than 0.05, so we say that the relationship is statistically significant. The r-squared of 0.172 indicates that 17% of the variance in the model is explained. The f-value of 9.972 with 1 and 48 degrees of freedom has a p-value of 0.003, indicating that explanatory power of the model as a whole is statistically significant. A common mistake of students is to assume that a multiple regression is simply adding together the parts of a simple regression. Here I have some results reported. Later I'll go into what should be in an APA table of regression results, but I will give you a quick primer here. You will notice the names of all the parameters are on the left. Column 1 contains the unstandardized results of the simple regression using poverty rate. Column 2 contains the unstandardized results of the simple regression using temperature. The mistake comes in the third column. Students assume that since they ran two simple regressions, they have a multiple regression and need only add up all the results to get the answer. The beta coefficients from the simple regressions are moved over to column 3, and the constant and r-squared values are added together. This solution is wrong. The first two columns are correct, but not the third. Multiple regression is an entirely different entity from simple regression. It is not two simple regressions, but a new regression with two independent variables in the same model. The equations for a multiple regression with two variables are shown here. The resulting geometric object is not a line, but a plane. What simply adding together two simple regressions misses is that our independent variables are correlated among themselves, and this correlation must be factored into the model. In the case of our example, the Pearsons R between log of the violent crime rate and temperature is 0.569, a strong positive relationship. Let me use a Venn diagram to explain the problem and the solution. The area of the square represents what we have to explain, the total sum of squares for the log of the violent crime rate. The red circle represents the portion of the model explained by our first independent variable. The blue circle represents the portion of the model explained by our second independent variable. Right now, the two independent variables explain different parts of the total sum of squares. However, when independent variables are correlated with each other, there is an overlap. A part of each independent variable explains area also explained by the other independent variable. The formula of the beta in a multiple regression model includes a term that adjusts for this overlap. Multiple regressions are easy to run in SPSS and PSPP. The same command is used for multiple regression as is used for simple regression, only more than one independent variable is entered into the independent variable box. Here is the output for the example problem. We get the same output as simple regression, except when we interpret it, we must consider that the two variables are mutually controlled for the effects of the other. When multiple regression is used, the effects of a variable can stay the same or they can change. The possibilities are listed here. If one can imagine it, it can happen. The use of the word control is a bit confusing because the word has two different uses, so let me clarify here. First, multiple regression always has one variable controlling for the effect of another, and vice versa. Second, what we call the control variable depends on our intent. An independent variable is of theoretical interest, that is, it is specified in our hypothesis. A control variable is included in the model, but does not contribute to the theory. The computer does not distinguish between an independent and control variable. It treats both the same way as independent variables. Whether one or more of the variables should be labeled control is up to the researcher. Let's interpret the output. The equation of the line now has two independent variables. The coefficient for the poverty rate is 0.03 and for temperature 0.01. The constant is 4.73. The standardized betas showed that both coefficients are weak and positive. Neither variable is significant. Sometimes when a variable has a p-value below 0.10, we note the result is trending towards statistical significance. I'll draw attention to this issue again when we look at APA-style tables. The R-square of the model is 0.207. In other words, the model explains 20.7% of the variance. In this case, we also want to pay attention to R. Unlike the case of a single independent variable where the Pearson's R is the same as R, no variable has a coefficient equal to this R in the multivariate case. The R now is sometimes known as the multiple R because it shows the association between the entire model to the dependent variable. The multiple R is interpreted using the rules of standardized coefficients. So we conclude that explanatory power of the model as a whole is moderate. There is no direction with multiple R because there cannot be a negative sign with this statistic. The model as a whole is statistically significant, even though the individual variables are not. Here's what the results look like in an APA-style table. APA does not strictly control the content of the table, but the one I show here is a useful format for a beginner. Notice right away that I did not report the numbers on the output. They are rounded to significant digits, and the rounding rule is consistent. Each column represents an equation. It is useful to name the column headers with either names or numbers and then refer to the column header names or numbers when writing about your results. We move from left to right, moving from the simplest to most complex models. The title clearly describes the contents of the table. Somewhere on the table also mentioned the dependent variable so the reader knows, either in the title or if multiple dependent variables are used in the column header. We can use either beta or standardized beta coefficients. If we use betas, the constant term is usually provided as well, so the entire equation can be recreated by the user. If we use standardized betas, do not report the constant term. You may wonder which coefficients to use, but the decision is a personal choice based on what you want to communicate. Use asterisks to communicate statistical significance. The number of asterisks next to each variable communicates the significance level, and a key for interpreting the asterisk is placed at the bottom of the table below the third line. When a coefficient is not significant, there is no asterisk next to it. Note that I followed a common practice to use t for trending if the relationship is not significant, but the p-value is less than 0.10. Some professional statisticians add t or the standard error. These inclusions provide more detail for the reader, but they can also make the page more crowded. It is useful to also include a measure of the goodness of fit. Here I include the R-squared. I communicate the significance of the model using asterisks as well. I often say, once you can do 3, you can do them all. What I mean is once you can do a 3-variable model, a model with 1 dependent variable and 2 independent variables, you can do models of any size by simply adding more variables. The table here is quite complex. It has all the elements of a good APA table previously described, but with more variables. Each column is the model run for a different dependent variable, and the name of the dependent variable is included in the header. It is possible to have too many variables. So how do I know when I've reached that point? There is no set rule, but the equations shown here provide an effective guide. We solve both equations and choose the result with the lowest minimum number of variables. The solution is not perfect, but provides a good starting point. Multiple regression builds on the principles of simple regression to allow the creation of models with 2 or more independent variables. The need to remove correlational effects among independent variables creates results that are different from simple regression. Once you can do 3, you can do them all.